So, one across. It can occur in cells, but it is more fun at the organism level. Reproduction. Okay. Number 9 across. What the chemical reactions in your body are called. 9 across. Metabolism. So the sum of all the catabolic events and anabolic events. You're gonna put some food in your mouth, you're gonna break it down, it's gonna be absorbed into your blood. Your liver is going to receive it and decide what the heck to do with it and go build some enzymes, build some muscle. What do you need? So from your proper nutrition, you're going to build things up. So metabolism is the combination of all the chemical events that happen in your body. Okay. What makes nutrients useful? Oxygen. So, if you're on the keto diet and you've decided you're sworn off carbs for forever, not condoning that at all, your body's going to figure out a way to make glucose. But your nutrients are to make ATP. They're so you can make energy. You have to have oxygen to make the majority of your ATP. Yes?
How bad is that keto diet for you?
Well, so I actually, last semester, I had my AP2 students do a debate, a pro and con debate on it. So in my opinion, any diet that you have to continually check your ketones or else you're poisoned, I don't think that's right. Yeah.
Considering most people don't have medical equipment in their house.
Yeah, it's like a urine strip where you just urinate on the strip, and if seriously, the ketone, this is how we check cats and dogs for diabetes. I mean, we do blood work too, but if they're to the point that they're spilling ketones in their urine, they go to the ER. So ketoacidosis is what kills uncontrolled diabetics or infection. But let's say you've just developed diabetes, and you know something's wrong, but you don't have insurance, so you just don't want to go to the doctor, and you just get worse and worse and worse, you're gonna die.
You think that'd be talked about more considering how huge the keto diet is?
Yes.
It doesn't matter of natural selection at that point.
Well, and it sounds like my daughter.
Not
I
fair.
think that it's my understanding from the debate that it has been kind of balanced a little bit in that there's different levels of keto diet and not completely swearing off of all carbs. And you know, you should always have vegetables because you need that fiber. Maybe some whole grains, let's say quinoa, you know, wild rice, things like that. So I guess it depends on which
They're
level.
high in carbs and amino acids.
Say that again.
Things that are high in carbs and amino acids.
Amino acids, and then even, you know, you gotta have the proper fats. I mean, and just in general, dieting is, it always seems like it's such a mystery. It's just as we get older, you'll hear me say this at the end of every system chapter. As we get older, things just don't work like they used to. We don't make the proteins like we used to. So we don't need as much food. And, you know, we just have a tendency to put on weight if we don't exercise and eat properly and if we eat too much. And Americans in general love food. So. Good question. Okay, 11 across. What you need to run fast and jump high. 11 across. Nutrients. For this to, 12 across, for this to occur, constructive activities must occur faster than destructive activities. So 12 across would be growth. Anabolism. you have something, let's say you had a human being that their anabolism was twice as high as their catabolism, what part of life do you think they're in?
Puberty. Puberty.
Puberty, yeah, just growth, they're still growing. Okay. A term referring to the kidneys, 13 across, would be renal. 14 across, what has to happen for an hour before you swim? So that would be digestion. So that's actually true, that's not a wives' tale. You should definitely wait before you're done, before you go with any activity, but you know, swimming, you're gonna drown if you get cramps. And you'll see when we get to the autonomic nervous system, when you eat, you tell your body to go into parasympathetic mode, rest and digest. You've told it to do that. So your blood supply is gonna shunt to your GI tract. Your blood's gonna rush to your digestive system so you can digest your food. So that means if it's all pooling in your digestive system, it is not pooling in your muscles. Swim, 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 cramp, you're in water, you drown. So that's true. All right. Okay, so tips down. Changes occurring during the first 9 months is embryology. This next one is the one that I say is actually a term from the old book. Not grumpiness, but responses to changes in the environment. So the old book was irritability, now it's responsiveness. So my bad, they need to fix that, Mira. If you couldn't find the answer for that one, it's not in your book anymore, that's why. Number 4, regulating lifelong functions, negative feedback. So I didn't think that was a very good question either, because I would just put homeostasis, and you look at that, you're like, homeostasis doesn't fit in that. Organs in relation to each other / structure is anatomy. Anatomy is structure or form. Physiology is the way that it works or function. The substance that makes up the most of us, 6 down, water. We are watery, proteiny people. You're going to learn how to make proteins in lab in about 3 weeks. How body parts work together. 7 down. 7 down. Physiology. And then dynamic equilibrium. 8. So why dynamic equilibrium? Well, because things are always changing. Our environment's always changing. What's going on the inside of our body is always changing. And we always have to make it within a normal range for the human body. Okay. So, all right. So I know that y'all did what I said, and you went and watched my lecture, went over your notes, things like that, right? Yes. This happened last week, didn't it? My phone wouldn't ring. Was that in this class? Yeah. Very nice. I don't know if y'all been through this, but here's a little study tips PowerPoint. Every now and then I'll get somebody say, how do I study? Look at this.
I'll learn how to study.
Yeah, there's all kinds of little things in here to help you out. Checklists, reading tips. Reading, I can't even stress enough how important reading the textbook is. You wanna understand it? Read the textbook. Because PowerPoints are just like highlights. The book is full sentences, context clues. That's how you're gonna learn. And listening to me. Falling asleep, then you need to go get some coffee and come back. Or sometimes Miss DeAngelis makes people do jumping jacks. I don't wanna make y'all do jumping jacks. That's who you have, right, for lab, Miss DeAngelis. She'll make you do it if you look like you're not paying attention. All right. So I think we finished at pH, right? So tell me something that you learned with your reading and your listening about pH.
Concentration of hydrogen ions.
Perfect. It's measuring concentration. This is concentration. Write that up. Of hydrogen ions. Okay. So the scale goes from 0 to 14. This side, 14, is alkaline, or you might see it written as basic. And then this side is acidic. So what would be neutral? If you got 0 to 14.
7.
7. Perfect. 7 is neutral. All right. So what people get confused with is when you say the more acidic it is, so I'm talking about more hydrogen ions, the number goes down. Okay? And people get confused with that. So let's say a pH of 1 is going to be this. And so what I ask you is, would you rather have this much money, or would you rather have this much money? So which much money would you have? You had one choice, you gotta pick one. How much money would you want? The bottom one. This would be equivalent to pH of 1, that many hydrogen ions, okay? If it's this, 1, 2, 3, 4, 5, we got a pH of 5. And so when you're looking at it, I think I already erased it. So this is like 10 to the negative 1. This would be 10 to the negative 7. So it's like the zero, the zeros become more behind the decimal, okay? So I don't know how better to explain that. Even in AP2, it's gonna come up again. pH comes up again, and I know it's hard. But the lower the number, the more, so from the scale of 1 to 14, the more hydrogen ions there are. And when you see hydrogen ions, think acidic, okay? Hydrochloric acid. Hydrochloric acid, when you see hydrogen ions, think acidic, okay? Let's go and make that bigger. Did all that, right? We got to, oh wait, did we do buffers? Did we do this?
No.
Okay. So we stopped at salts, right? Because I've already been through salts, acids, bases. They ionize in water, they ionize. They're going to either lose, transfer away electrons, or they're going to gain electrons because they've been transferred to them. Ions, if they're positive, they're called, positively charged, they're called cations. If they're negatively charged, they are anions. Let's see. So we've done all that. And also, ions are going to create an electrical current if you set them up with the, which we will do in lab, set you up with the correct electrodes and the light bulb and everything. So the water solution, the solution with salt or any acid or any base is going to create a current. So hopefully you'll turn on an ion, turn on the light bulb. Organic things are not ionized. Ionized things, salts, acids, bases, carbs, proteins, lipids, nucleic acids are not going to ionize, okay? All right. Okay, so because, what did we say about that crazy hydrogen right there? What's his atomic number? 1. So therefore, he has 1 proton, because that's the atomic number. And what's his atomic mass? 1.
0.00795.
Yeah, we'll just go ahead and we're round them. So if it's got 1 proton, then it has how many electrons? 1. And then while we're at it, if you have an atom that has an atomic mass of 1 and its atomic number is 1, how many neutrons does he have? 0. So what happens often is this little electron transfers to somebody else. So now all that's left is a proton. Acids are often called proton donors. And then bases are called proton acceptors. Bases are usually going to have a hydroxyl group. So this is called a hydroxyl group. Let's see. Not a chemistry class. Can you do that? We're not going to go any more into acids and bases. The important thing is we're going to see how they work in the body. And you need to understand, when we get to the cell section, what an ion is, a charged particle. Charged particles can't go willy-nilly into a cell because they are charged. Why are they charged? Because we're watery people and it got broken up. And so now it's floating around in our body as an ion. Did I talk about the inside of a cell membrane yet? What did I tell you about the inside of the cell membrane? The very inside. Did I mention it? Yes. So we've got this, what is this molecule called right here? Phospholipid. I don't think I've told you. So these go all the way around. The very inside of our cells have voltage. And I'm just going to use this average number because the majority of the ones that we're going to work with are this, -70 millivolts. So we have electricity on the inside of our cells. So we don't want somebody coming in willy-nilly or leaving willy-nilly because it messes with this. And this has to be ruled so that we can control muscle contraction, so that we can fire a neuron. You'll see it later. But we don't want charged particles going willy-nilly in and out of our cells. So this boundary is important for so many reasons. We don't want to mess with our factories. All right. This right here, what's the difference between a strong acid and a weak acid? So on the left here, we have hydrochloric acid. It's a strong acid. A strong acid completely comes apart, dissociates within the water. So this, what is the universal solvent? Water. So then hydrochloric acid would be the, what's it called? Solute, yes. So he completely comes apart. So all the H's have separated from the Cl. If it's a weak acid, like this is acetic acid, some of them are going to come apart and some of them are going to stay together. Is the water bound to this? This is a review. Is the water bound to this hydrogen ion? No. It's a solution. So they're living together, but let's do, here's my sodium right here, and the water molecules surround it, right? So remember mixtures?
They're not bound to each other. Solutions, what's the other two? One starts with a C, colloids, and the next one starts with an S, suspensions. So you've got solutes mixing in with solvents, but they're not chemically bound. So sometimes matter bonds, ionic bonding, covalent bonding, hydrogen bonding, and sometimes they just coexist together. All right.
So, same thing with bases. A strong base would completely come apart in water. A weak base would not. What do we have in our stomach? Do you know? Acid. And it's hydrochloric acid. It's a very strong acid. And our stomach is protected, which you'll learn about all the different layers of the stomach and everything. But why doesn't the acid just eat up our stomach? It is made so that that doesn't happen. But where's the next part of the passage? You swallow your food, goes down the esophagus into the stomach. What's next? Small intestine. The small intestine is not made the same as the stomach. So, what are we gonna do? You're gonna have to stay in homeostasis. Here comes that chunk of food that you have chewed up, swallowed as in a bolus. Now it's been mixed around, it's gonna be called chyme. And that little bit of chyme is gonna go into the duodenum with the hydrochloric acid. But I'm telling you, it's really acidic. And the duodenum is not made like the stomach. So, what's gonna happen is, we are going to have hormone signaling. There's that endocrine system that goes, well, hold up, we can't have this hydrochloric acid, so I'm gonna send a signal to the pancreas to release a buffer. And that buffer is gonna get squirted into the duodenum and mix with that chyme. And buffers change strong acids into a weaker acid. They don't make an acid a base, but they make a strong acid a weak acid. So therefore, the duodenum doesn't get an ulcer blown into it because homeostatic mechanisms, we've got hormones that go, okay, here comes some hydrochloric acid, pancreas, I need you to release this buffer, some bicarbonate, it gets squirted into the duodenum, mix, 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 and it moves on. So, who's the two main control centers for homeostasis? Endocrine and nervous system. Very good. So that's all. I know I have probably too much information on the buffers right on here. We've got a lot of buffer systems in our body. Don't memorize that. We're not going to do that for this test. But you do need to understand what a buffer system is. As we go through systems, more in AP2, honestly, we're going to point out some buffers. I just pointed out one in the digestive system, which we just finished in AP2. All right. So we talked about this. Blood is 7.4. I put ish because it depends on if it's oxygenated blood or deoxygenated blood. So there's a range. AP2. All right. So I'm not even going to go any further than that. You tell me what the 4 organic groups are. Be brave.
Proteins.
Proteins.
Carbohydrates, nucleic acid, lipids.
Carbs, nucleic acids, and lipids. Did y'all know this already? Have I said it in this class? Yes, I've said it repeatedly. If you don't know this yet, you need to listen better. Okay? This is not going away. We are organic people. We base our nutrients on what we need to make for our body. Okay? So, we've got monomers. So this is a whole chunk. If I got a turkey leg, that is a giant chunk of amino acids shoved together. Darn it, I didn't want to say that out loud. It's a big chunk, and I need to break it down. I can't absorb into my bloodstream from my tube, known as intestines. Can't get that into my bloodstream unless it's smaller. So, the smallest molecule that our food groups can be broken down into is called monomers. So what is the monomer of a protein?
Nucleic acid. Amino acid.
Amino acids. So once my turkey leg has gone through the churn in the stomach, and the right enzymes have shown up to break that turkey leg into individual amino acids, now I can get into my bloodstream. Carbs. What is the monomer of carbs? Monosaccharides. And which one do I keep mentioning as like the ultimate for ATP production? Glucose. So glucose is the one that has a tendency to come up a lot. When we get to ATP2, we're going to talk about all of that. Okay, this one is nucleic acids are probably a little bit foreign because you don't think about that as one of your food groups. But do you know what the monomer is of a nucleic acid?
Nitrogenous base.
It's going to have a nitrogenous base, so I am going to write that. N base. It's going to have a name. It's got a sugar, which is going to be a ribose sugar or a deoxyribose. So I'll put a pentose sugar. How about that? Pentose sugar. And then a phosphate. So this is called a nucleotide. Okay. And then lipids. Actually, its final breakdown product is 2 molecules.
Glycerol.
Glycerol, very good.
Fatty acid.
And fatty acid. So it depends, fatty acid. It depends on what type of lipid as to how many fatty acids. Depends on which carb, so that we can figure out what monosaccharide. It depends on which nucleic acid and which section of the nucleic acid as to what that nucleotide is going to look like. And we actually have like 20 amino acids. Okay. So I'm gonna have to reference kitty cats. Kitty cats need a certain amino acid, or else they're gonna die. Their heart gets really big and thick, and that amino acid is not in tuna fish. It's called taurine. And so a long time ago, people would just open up a can of tuna and feed it to their cats instead of going to the store and getting cat food. You know, it's cat. It's the mentality of life. Well, then we figured out all these cats that were dying of heart failure, they're missing an essential amino acid that must go in your mouth. It's essential. It means it has to be eaten. Your body can't make it. So, let's see. So let's go through here. Let's do real quick. We had 2 major equations. One of them, so we had 3. Exchange was one of them. Let's skip that one. What is the other 2 equations? Decomposition. Very good. And synthesis. I heard it. Good job. Okay. In biology, we're going to use water a lot to help decompose things and to help synthesize things. Let's talk about this real quick. If I have a decomposition reaction, I'm talking about metabolism, which, what is it? Decomposing, so I am catabolic. Very good. I'm breaking down. And if I am breaking bonds, what about the energy for this equation? Releasing. So that would be called exergonic. Very good. Now I'm going to tell you, if we're breaking things apart, it
biology, a lot of times we're gonna be using water. It's going to be called hydrolysis. So whenever you see the term lyse, from now on in your textbook, you should think break. So hemolysis means that something is breaking your red cells, for example. In the lab, you're gonna have a cell next week, right? Or is it this week? This week? Okay, there's a lysosome. Do you know what's in that? Digestive enzymes that can destroy things, including the cell. It's all wrapped in phospholipids, it's all boundaried up. But if you get a hold of that lysosome, then all the enzymes come out, it's gonna to that cell. If that's its job. Or if you have a disease. But anyway, so whenever you see lyse, you should think split. And if I'm saying hydrolyze, so a hydrolysis, that's water is lysing something. I'm breaking things apart. So I'm not giving you a new equation, I'm just adding to the equation that you already know. In biology, water does a lot of this. And then likewise, let's go through synthesis. What do you know about synthesis reactions? Anabolic, because if you're synthesizing something, you're building something, you're building up something. And so therefore, if I'm building things, if I'm attaching things together and making a no bigger molecule, I'm creating bonds. So energy-wise, that would be a endergonic reaction. So storing energy in bonds. We should put over here breaking bonds. Oh, messy. Bonds. There. All right. So, with synthesis, what you're actually going to do in biology, a lot of times we're going to take out a water. So we're going to dehydrate it. So sometimes what we call dehydration synthesis, because it's all about the water. I'm going to show you some pictures. Okay, this is a very simplified picture right here. So I'm going to explain a couple of things. I will never ask you to draw these compounds. This is like in organic chemistry, this is an understood carbon right here, right here, right here, right here, right here, right here. So these are all understood carbons. And this is showing sticking off of here an OH. On this side is sticking off an OH. Okay, so this is one molecule, here he is again. If I am going to take out a water, I'm going to sneak this H away, sneak this OH away. They're going to bond together and out goes the water. I dehydrated it. And then what's going to happen is this oxygen is going to come and link over to this side. So I had 1, 2 molecules, and now I have 1. So I have built up something. I have synthesized something anabolic. I created bonds, so endergonic reaction. And how did I do it? By dehydrating it. Here's this thing's been naughty. There it is. So this right here is being dragged down here. Let's add some water. I'm going to use water to lyse these two things apart again. So I'm going to add water. This hydrogen is going to come and sneak and attach to this oxygen, and this OH is going to come and attach where the oxygen was. Boom, boom. I have broken it apart. Catabolism. I've broken some bonds and added water. Okay. So I'm not giving you anything new. I'm just telling you in biology, decomposition is often done by water. In biology, a lot of synthesis reactions are done by taking out the water. okay? Not new, just adding to what you already know. All right, so carbs, very important. Adults, us right here, carbs we get is where we get our energy from. Children use a lot of fat. So children are growing, that's a whole nother class. Is, you know, there's pediatricians or their own doctor, right? You don't take your 3-year-old to internal medicine person, you go to a pediatrician. They're different. So the one that I really want you, well, I guess two that I really want you to focus on. I already said that the monomer is the smallest unit of the monomer of carbs is a monosaccharide. That's a single sugar. A poly, whenever you see the term poly, that's multiple. So does anybody have an example of a poly something? Polygon? Polymers. Yeah, plastics, polymers. How about kitty cats? Has anybody ever met a polydactyl cat with many toes? They look like they have mittens instead of regular feet. No? They're kind of cool looking. More weapons for me, but anyway, they're usually pretty sweet to me. All right, and if you ever see di, that's 2, right? If you ever say mono, that's 1, right? You already know that Latin base. All right. So, something that I have seen on the final is this, and so I left it in here. I'm not gonna ask you this, but I would highlight it for a potential finals question. This formula right here is the general formula for monosaccharides. What does that mean? Well, on this, how many carbons are in this right here? 1. It's assumed 1. And then hydrogen, there's 2. There's assumed 1 oxygen. Put it in parentheses and there's an N. Let's make that up. 6. If this is 6, then 1 times 6 is 6, C6. 2 times 6 is 12, H12. 1 times 6 is 6, so C6, H12, O6, glucose, okay? You could do it with a 5. Anyway, I've seen it on the test just like that. The general formula of CH2O parentheses N is for which organic group? There you go, carbs. Okay, so the hexo sugars are going to be the ones that are going to be in our food. So glucose is the one that's going to help us make ATP. Fructose, I believe that's like agave nectar and honey. I'm sure I'm missing some. And then galactose is one of the breakdown products of a disaccharide called lactose. You've probably heard of it. Pentose sugars are only going to have 5 carbons, so 6 carbons, 5 carbons. Ribose and deoxyribose. Have you heard that word before? Ribo, where? RNA and DNA. Ribonucleic acid, deoxyribonucleic acid. So, when we're talking about the monomer of nucleic acids, it's actually going to have either deoxyribose, DNA, or ribose, sugars, and that's going to be, ribose is going to be for RNA and ATP. I'm not going to ask you to draw anything. So polysaccharides, let me give you this class right here. This is something to remember forever and ever, because when these words come up in AP2, you should already know what they are. So if I said the word cellulose, you should know that they're in the carb family. So the plants that we eat, we're not very good at breaking down cellulose. In fact, we're going to poop it right out. But we need that fiber. You have bacteria in your large intestines that are working very hard to make you some vitamins. Did you know that? That your large intestines, your colon, has bacteria in there that have good work going on. But we gotta feed it. We have to feed them some cellulose. Starches is the carb that everybody's scared of. So breads and potatoes and things like that. So that is a carb that people are scared of. People aren't scared of eating vegetables, but maybe as Americans we don't eat enough, but you really need that fiber. Glycogen is not eaten, but I've mentioned it before. Do you remember what glycogen is? It's sugar / glucose plus another glucose plus another glucose plus, so what is it? It's how glucose is stored in the liver and some in the muscles, because you're going to be studying so hard for your anatomy and physiology test that you're going to forget to eat, maybe. And so your blood sugar is going to drop and your body's going to go, well, hold up, we're losing homeostasis. Liver, get busy. Take that glycogen, catabolize it, and let's get some glucose in that bloodstream, because this person is studying so hard they forgot to eat. So glycogen is not eaten, but it is a carb. Lipids. So the three classes for the lipids that we're going to talk about, 3 types: triglycerides, is what we think of as fat, triglycerides. The steak, the delicious steak with the little strip of fat around it, triglycerides. Phospholipids, you already know where that is, right? I mean, it's in lots of places, but the one thing that no cell is missing is that phospholipid bilayer that's protecting it. And then steroids. There's eicosanoids. We're not going to talk about eicosanoids. So what are triglycerides good for? Where they're a good backup plan. Like, bears go and hibernate and they're sleeping for months on end, and they're going to use their triglycerides to keep them alive, just for example. We're going to use it for insulation. So, back when we were nomads or whatever, right? You store as much food as you can and you eat while everything's wonderful, but you go through the winters just like the animals go through the winters. So it's helping you stay warm. Very, very thin people get cold easily. And then protection. That's something that we don't really think about very much, but there's actually a layer of fat over your kidneys that are helping there's multiple things keeping your kidneys in place, but fat is actually one of them. And then you have a little bit of fat around your heart. So fat is actually for protection too. Triglycerides are going to be 3 fatty acids in a glycerol. Phospholipids, those 2 little tails, those are the fatty acids, so 2 fatty acids in the phospholipids. So let's look at this. Here is just 1 fatty acid. Here's 1 glycerol. What are we doing? We're dehydrating. Yeah, dehydration synthesis. I'm going to take out this H. I'm going to take out this OH. So for fat, triglyceride type fat, this is what it looks like. So up here, I've taken out an H and an OH. But if I have 2 more of these and then take away an H from 2 more of these, there I have built a triglyceride. Let's say I want to lose some weight. I want to lose some weight. I want to get rid of some of those triglycerides. What is going to decompose those triglycerides? So if you're dehydrated, you're not taking in enough water, you're going to have a heck of a time breaking down that fat, because you need water to hydrolyze this triglyceride into 3 fatty acids and a glycerol. Does that make sense?
Can I ask something?
Yes.
For the one where it's dehydrating, if it wasn't highlighted, can you explain again how we'd know? Just the fact.
Oh, I would never put that on the test. I'm not going to draw that or anything. You just have to understand the concept.
Like, if I take out of water, I'm linking some molecules together by taking out an H and an OH from each of those individual molecules. But I'm never gonna ask you to draw anything. I'm not gonna put molecular formulas on there. I just need you to understand the concepts for this test. But, ask me your question again.
If it wasn't highlighted, how would we know it was dehydrated?
Well, I guess you could compare this. Now, it would be easier if all 3 fatty acids were there. Compare this to this, and what's missing? So up here, the glycerol had an OH, and down here, the fatty acid had a C double bond, C single bond, OH. What's missing? Still got that double bond to an O, but I'm missing an OH here, and I'm missing an H here. So just comparison. But I would never have you do that. That's chemistry. All right. Whenever you see something like this that's got a video, obviously you can't play it in PDF, and I can't play it from OneDrive. But I leave them in there if I think they're good videos, so that you, in the study area, remember in mastering, study area, animations and videos, go find the video to help you. You know, a lot of people say, well, I'm really visual. Go find yourself a video. There's lots of study stuff in there. Okay, as far as fats go, so when we say a saturated fat, what that means in chemical terms is the carbon is saturated with hydrogen. That's what that means, although it's linked to another carbon or whatever. So I'm not going to ask you that, but what I would like you to understand is a saturated fat is going to be relatively solid at room temperature. So can you think of a saturated fat, a fat that you think of at room temperature? Butter. How about that thing that I alluded to a minute ago? No. Steak fat. So this is another way, so I showed you that little ring a minute ago that had the understood carbons. Whenever you see something like this with these lines like that, this is an understood carbon, this is an understood carbon, this is an understood carbon, with single bonds going from carbon to carbon. This is a double bond to oxygen, but it's assumed that there is a hydrogen, 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 hydrogen saturated with hydrogens. That is not a test question, but that's where the term comes from.
So the little triangles just mean X times whatever the letter is above it then?
Little triangles. Like these things?
Yeah.
This is like a carbon bound to a carbon, bound to a carbon, bound to a carbon, bound to a carbon. So that's kind of chemistry. Just like that ring that I showed you earlier for the hexose sugars or whatever was they don't write C because it's organic chemistry, it's understood. This is not an organic chemistry.
Okay, sorry, I'm just trying to understand. So the triangles, there's that many of the O's then, or am I overthinking this?
So there's understood hydrogens off of these. Am I explaining that right, Ms. Papadopoulou? It's organic chemistry. So we've got, as with this chain, it's understood carbons, and whenever there's nothing written there, it's understood hydrogen. And I hate that, it's a biology class. But I have to explain how it's saturated, not saturated. What I want you to know is at room temperature, saturated fats are fairly firm. Unsaturated fats mean it is not saturated with hydrogens. So what's happened here, there's a double bond between those carbons. So there was potential for it to have a link up to another hydrogen, but he chose to double bond. Instead of using that bond for a hydrogen, he gave an extra one to the carbon. So now he is unsaturated with hydrogen. And what that does is it creates a double bond, creates a kink. So you can see how it's not straight anymore, it's got a kink. And because of this unsaturation, I am now liquid form at room temperature. So for biology purposes, if you hear the term unsaturated, then unsaturated fat is going to be liquid at room temperature. So can you give me an example of something like that?
Vegetable oil.
Vegetable
olive
oil. Perfect, olive oil, yeah, the oils. Okay, phospholipids, we've already done this. So we've got a head, that's the phosphate group, and then we're gonna have tails that are the fatty acids. The head is hydrophilic, the tails are hydrophobic. Have I said that in this class? Do you think it's important? Yes. Looky here, one of these fatty acids is straight and one of them is kinked. So this one is probably saturated and this one's got a kink, so he is unsaturated. That's the only time you'll ever see that in this class. What you need to understand is it's a lipid, and so therefore that section right there is hydrophobic. Okay, steroids. So our body makes steroids, and then very quickly they're going to become something else. So cholesterol is the one that we're going to talk about in the next probably chapter or two as our most important type of steroid. We'll do more in AP2 a little bit, but cholesterol, well, first of all, let me talk about that phospholipid bilayer. That phospholipid bilayer, it looks like they're all just these little toy soldiers all lined up, doesn't it, on that piece of paper? But do you know what they're doing all the time? They're dancing. They change places and they're moving around. Sometimes you'll see it called a fluid mosaic. And with all that movement, could potentially be a rip. But thanks to cholesterol, it actually is embedded here and there throughout cell membranes that help stabilize it and help keep it from breaking. Isn't that crazy? Those little guys dance. No kidding. All right. Cholesterol, you always hear about how cholesterol is bad for you, but actually HDL, that was what the cholesterol that our liver makes, is good for you. It's a building block for your bile, and it's a building block for fatty, blank, need some more tea, need some more coffee, fat-soluble vitamins, ADEK. And it helps you make, we have different kinds of hormones, but some of them are cholesterol-based, sterol-based, steroid-type hormones. So if you want some estrogen, you want some progesterone, you want some testosterone, you need some cholesterol from your liver. Very important lipid, yes.
So this might sound like a stupid question, but whenever you're using anabolic steroids, is it enhancing your body's natural steroids, or is it adding another compound to your body to feed off of?
I actually don't know what it does to your liver's metabolism.
Oh.
That's a great question. I'm going to actually, yes I do. Anabolic steroids, here's a reason to not do anabolic steroids. Men that abuse anabolic steroids get very small testicles. So that must be a negative feedback because the bodies are...
For a short period of time.
Huh?
For a short period of time.
For a short-
That's normal after a while, right? It does.
Okay. But yes, so that would tell the body, hey, I already have steroids, so I don't need to make so many steroids, so then you're not producing as much testosterone. So yes, you make me think that through, but good question. I had to think about disease.
Testosterone levels go back to normal. That's when you start doing post-cycle therapy where you're blocking off estrogen that's building up in your body naturally instead of testosterone. So then your body starts leveling out again. But if you do it too often to where your body completely shuts down the testosterone, then yes, then
It's
issue
permanent.
does happen.
So when is the time that you're just doomed? How long?
When you start getting, oh good lord, what's it called?
Breast development? Or-
Yes.
Okay, so
If your
that,
body's producing so much estrogen because it's not naturally producing testosterone,
then you're doomed.
it's a
Not
good time
reversible
to slow
anymore.
down. It's a good time to slow down.
It's good time to slow down. Funny. Learn something new every day.
I was going somewhere with that and I completely got off track.
Okay.
So there are certain types of steroids that help you break down and help you build up while
Yes.
breaking down. So you have like Trenbolone that helps you burn fat really fast but helps you build lean muscle, or you have
Catabolic.
DECA that helps you retain more water for your muscles to build more. So that's why I was wondering the breakdown portion, because we call it anabolic steroids, but it does break down some portions of your muscle and fat.
And there are different, I'm not familiar with DECA, but could DECA also have a catabolic type steroid scheme?
So that one, I think it just mainly helps you retain water a lot more.
Because catabolic steroids make you retain water.
Then that's probably what it is.
And our body makes, our adrenal glands make cortisol. You've heard of the stress hormone cortisol, and it's good in normal amounts. In excess amounts is when it starts destroying things. So diseases that cause excess cortisol. When you get into poison ivy and you have to take some prednisone, so in the steroid family, you should take it in the morning so as to not confuse your adrenal glands, because your adrenal glands make it in the morning. So if you take it at night, the next morning your adrenal gland is going to go, oh, I still got some floating around, so I don't have to work. And so you could actually shut down your adrenal glands by not taking steroids correctly and for an extended period of time. So if you did it every night for 5 days, that's not what I'm talking about. This right here is a steroid structure. Why am I showing you this? Because maybe for AMP2, you're going to have Professor Martin or Professor Johnson. So they refer to steroid bases as stop sign, stop sign, stop sign, house. Okay? So I'm showing it to you. So this won't be the, so AP2, if you don't have me, you have somebody else, and you hear stop sign, stop sign, stop sign, house. You don't know that? You do now. I don't use that term, but I know that Professor Martin uses it all the time. Do what?
I'm finally understanding somebody today. Stop sign, got it.
Oh, can I help you with something?
No, I'm
No.
lost.
Start the entire semester over.
Well, we're gonna review, oh, and that brings me to, tomorrow, in this room, I have 2 AP1 classes. I have an 11 a.m. and I have a 12:30. And because they didn't have Monday off, they were Tuesday, Thursday classes, then they're gonna have more time to review. And you are more than welcome to come and sit in on that review if you want to. 11 a.m. and 12:30 in this room. Okay, proteins. So notice I have this N, like underlined and bolded and lots of asterisks. So we're organic people. What are the 4 most common elements in our body? Carbon, hydrogen, oxygen, nitrogen. Okay. Nitrogen is going to come from both the proteins and the nucleic acids. So when we say the urinary system is eliminating nitrogenous waste, that would be catabolism of what 2 major organic classes? So I'm saying in the urinary system, we're going to say it releases, we're getting rid of nitrogenous waste. That would be catabolism of what 2 organic classes? Proteins, nucleic acids. Very good. Okay, what do I want you to know about proteins? We're very proteiny people. It's very important for our structure. You're gonna see protein inside the muscle, you're gonna see proteins inside the ligaments, you're gonna see proteins inside of all the connective tissues. What else? When you see the word peptide bond, okay, so I'm telling you organics bond by covalent bonding. Did I not say that? Okay. In proteins, that covalent bond's name is peptide. So if you ever see the word peptide, we're talking about proteins. So 1 amino plus 1 amino coming together. Now I have a dipeptide, not a diamino. dipeptide. I didn't do it, I'm not in charge, but it is something that you're gonna see over and over and over again from now on through AP2, peptide. If you see peptide, think protein, okay? Okay, so we've got lots of different kinds of proteins in our body. This would be structural. Do you want your skin to stay all nice and beautiful and supple? You want more collagen underneath this part of your skin right here. Enzymes are proteins. We're very proteiny people. We're gonna meet all kinds of proteins, and I'm not gonna belabor the point, and I'm not gonna put on the test, list different kinds of proteins, because you'll see them as we go through. Structure, I'm never gonna ask you to draw the structure, but this is the structure of an amino acid. So we've got 20 different ones, and they differ by this little section right here. Oh look, here we're gonna bond them together by taking out of water. Woohoo! Now I have 2 aminos stuck together. I'm gonna break them up, hydrolysis, add water. Okay, I am gonna ask you, well, I don't know. Proteins come in different shapes, so if it's just a line of amino acids, that's a primary structure. If it's got a twist to that line, or if it's pleated like this wall, that's going to be a secondary structure of protein. Let's take that twist, and I twist it more and wad it up on itself. That's going to be, what do you think? Tertiary. And then if I take a couple of tertiaries and stick them together, then that's going to be quaternary. So do you know when you take that secondary one and I've got it twisted, and I'm going to twist it some more. Maybe you've taken string before and twisted it until it starts wadding up. Do you know what's keeping it stuck together in that wad? Hydrogen bonds. Yeah, hydrogen bonds. All right, so got some pictures. This is just a straight line, that's primary. Twist it a little bit, that's secondary, or the pleat, like this wall, secondary. But if I start wadding it up so much that it becomes a bigger wad, that's gonna be tertiary. And if I take 2 tertiaries and stick them together, that's a quaternary. So we have structural proteins that provide structure to our body. They can be any shape, but most of the time they're more fibrous than globular. Globular is just like it sounds, a glob. That tertiary and that quaternary, they look like globs. And as we go through different systems, we'll say a globular protein, a structural protein, blah, blah, blah. And it's just like it sounds. If it's a structural protein, it's providing structure. If it's a globular protein, then it looks like a glob, and it usually has a specific purpose. So like enzymes are usually globs, okay? But as we go through systems, then, and we say globular protein, then what should come to your head is like, okay, that guy's got, he's not just structure, he's got work to do. And then proteins can be broken down with excess heat and then excess changes in our pH. So if you get really sick, let's say you don't go to the doctor, you've been throwing up for 7 days. You're not eating anything, but are you still throwing up something?
Yeah.
Yes. Hydrochloric acid and some water and some electrolytes, and you're losing that acid. Your body is becoming too basic. You're gonna die if you don't get that fixed. Okay. So whenever our acid-base balance gets messed up, it's like we fried the egg. I am not the egg out of the casing anymore. I've denatured, you actually have denatured the albumin inside that egg, which is a protein. Enzymes, we've actually already mentioned them as catalysts, but what do you remember about enzymes besides, well, what is a catalyst? There's one thing about an enzyme. What is a catalyst?
Speeds things up.
Speeds things up, and it makes it use less energy, so there's one thing. What else do you remember about enzymes? They do not get used up. So I drink some milk. I've got some lactose. Here's my lactose, my lactase. I'm gonna break up that lactose. Good job. I'm gonna break up that lactose. Good job. I'm gonna break up this lactose. Good job. He just keeps getting, doesn't get used up in the equation. Now here's something else. Enzymes are proteins, globular proteins. They usually end in ase, and they are very specific. So lactase is not going to break down maltose. Lactase breaks down lactose. Does that make sense? Change the energy. There's that picture again. Awesome pictures. Oh, look, there goes the water. So this amino acid, thanks to this enzyme, now has been dehydrated and I have synthesized a dipeptide. Thanks, water. Okay, nucleic acid. So we've actually already said this. If I am deoxyribonucleic acid, what is my pentose sugar? Deoxyribose. Ribonucleic acid, ribose. ATP is going to be ribose. So, and then the nitrogen base is going to vary. So let's look at DNA. DNA, maybe you met it in high school or something. It's like a twisted ladder. So on that ladder, we've got sugar, phosphate, sugar, phosphate, sugar, phosphate. You get the idea. What's the name of the sugar? Deoxyribose. Sugar, phosphate, sugar, phosphate, sugar, phosphate. And then we're going to have these little nitrogenous bases sticking off right here. C's go with G's. And A's go with T's. So the 4 bases are adenine, thymine, cytosine, and guanine in DNA. 2 sides to the ladder, and then it just twists. And do you know what's holding those 2 guys together? Hydrogen bonds. All right, let's do RNA. The difference in RNA is it's one-sided. It does have G's, it has A's, it has C's, but then it does not have T's. It has a U, right? It has a U, which is uracil. Okay, that's going to make a whole lot more sense when we're doing chapter 3 and you're making some proteins, because you're going to have to learn how to, nope, never mind, it doesn't matter. But A's always go with T's, G's always goes with C's in DNA. And then RNA, it's single-stranded. Instead of being deoxyribose, it's ribose. And instead of thymine, it's uracil. So what would uracil pair with? If I say DNA, A's go with T's and C's go with G's, what would a U go with? An A. And then finally, ATP. This is how we're alive. And it's crazy, actually. How can something so simple be like life-giving? So it's going to be a ribose sugar. And then it's going to be an adenine. And it's going to have 3 phosphates. Adenosine triphosphate. I'm very much simplifying this. I will never have you draw anything. But the way that we live is by breaking off a phosphate. So I had ATP. I'm going to have an enzyme. Do you know what his name is? What does most enzymes end in? ATPase. It's going to break that ATP into ADP, adenosine diphosphate, and an inorganic, I don't know why we have to do that, inorganic phosphorus. Is there organic phosphorus? I don't know. But anyway, that's how it's usually written, PI. And what would you call this reaction? Just give it a name. I just took that ATP and I cleaved off of phosphorus, what's in the reactants in the product. Catabolic, I broke it down, did I not? Okay, so what made us alive? By cleaving this off, I broke a bond And what happens when you break a bond? Yes, we release this energy that keeps you and me alive. Just by breaking off a phosphorus group. Isn't that insane? That's what keeps us alive. You're not gonna have to draw that, but that's what it looks like. And ATP helps us do all kinds of things. That's gonna be for a later date, a different test, but these are just examples of how it helps things happen, okay? So, I have to do roll. Okay, Rosa. Anaya. Syra. Dallas. Clarissa. Elizabeth. No Elizabeth. Kaylee. LaRonda. Ethan. Yadira. Belinda. Charles. Vidalia. Elizabeth. Robert. Mel. Dennis. Jade. Stephanie. Oh, Stephanie. Akeem. And Claudia. Alright, so instead of wasting time, or do you want to do learning catalytics? Yeah? Okay, we'll do that. Go ahead and don't open it yet, but go ahead and get your Wi-Fi going and go into course materials, but don't click on learning catalytics yet. I'm starting the session. Now you can go ahead and go on. You should see something, and here's question number 1. So the question, if you're struggling to get on Wi-Fi, I'll say the question out loud. Which of the following are subatomic particles found in the nucleus of the atom? Mark all that are correct. So we've got neutrons, protons, electrons, positrons, leptons, and gluons. Which of the following are subatomic particles found in the nucleus of the atom? What is in the nucleus? What's in the middle? Protons and neutrons, right? Where are the electrons? In a shell, right? They're in a shell. The outermost shell is called the valence shell. But we got 1 to 7-ish shells, I don't know. All right, next question. What subatomic particles are most important for bonding? A, protons, B, neutrons, C, electrons.
Where are y'all finding these questions? I couldn't get on last time, so.
Yeah.
Oh, darn it.
So I don't know.
Learning catalytics.
Where's that at?
So when you open course materials,
Okay. Show.
Oh, my master's.
learning catalytics.
Okay. Sorry.
That's okay.
The computers are a little much for me.
I'm sorry.
And if you don't have one, you know, you can buddy up with somebody. It's not for grade, you know, sometimes your neighbor says something that's like, oh, wow, I wish Dr. Wiggins would have said it that way. That makes so much more sense. So, who is responsible for making things fun? Electrons. What did we talk about, like with that outer shell? If he is not full, he wants to be full, right? How's he gonna get full? He's gotta go find some electrons somehow, some way. It's all about the electrons. That's what makes him reactive. Oh, this is so most of these questions I did not write, including this one. So if you don't have it pulled up, it's a salt shaker that is spilled over. It says, do you have 11 protons? Because you're sodium fine. I didn't write it, I just used it. The question is, which of the following statements about subatomic particles is true? Did I miss anybody when I called roll? I forgot to ask. I got everybody. I don't know which clock to believe. I don't know if I should believe that one or should I believe the one here, because this says it's just 1:45. My phone says it's 1:45. Okay. So the question, which of the following statements about subatomic particles is true? A neutral atom contains the same number of protons as electrons. That's true. On here, he's created as an atom, he's neutral, showing his properties. However, when he meets the real world, those electrons might have different plane. But the way you figure out if he's got a full outer shell or not is because the number of protons is the number of electrons. How do you know the number of protons for an atom? The what? Atomic number. The atomic number is the number of protons. Protons have about the same mass as electrons. That's wrong. Why? Electrons are so tiny, we're just gonna call them like almost zero. All right, see, electrons make up most of the mass of an atom. Who makes up most of the mass of an atom? Protons plus neutrons. So on your test, if I say an atom has this atomic mass and its atomic number is blank, therefore I just told you what the atomic number is, what is the number of neutrons? That's a very fair test question. And then the last one, protons and neutrons have opposite but equal in magnitude charges. What kind of charge does a proton have? Positive. What kind of charge does a neutron have? Neutral. No charge. So how could I make that a correct statement? Protons and blank have opposite but equal in magnitude charges. Electrons. Protons and electrons. Very, very good. Okay, well, we kind of just did that, so I'm going to skip that one. But it says never trust an atom. They make up everything. Let's do this one. In which type of chemical bond are electrons shared between two atoms of the same molecule? Electrons are shared. I also didn't make this up. I don't know who James is. Covalent
So if you see the term shared electrons, that's gonna be covalent. If you see blank electrons, that's gonna be ionic. Starts with a T. TR. TRA. Transferred electrons, right? And then what if I say I am sharing unequally? So I'm covalent, but I have a more specific name. Polar covalent. If I'm sharing equally, then I am nonpolar. Is polar or nonpolar hydrophobic? Nonpolar is hydrophobic. All right, I got one more minute. Let's see. Let's do. What type? That's okay. If you don't put it in exactly as the computer has, it's gonna say it's wrong, but I'll show you the answer here. We got 1 minute left. What type of mixture is blood? So what are the mixtures? Mixtures are where things are together but not chemically bound. We had 3 choices. We had solutions, colloids, and suspensions. So what is blood? Blood is a suspension. All right. So tomorrow at 11, tomorrow at 12:30, I'm here. We can do a review. And Claudia, can I talk to you for a second?